So we've got this really good population model for the total U.S. population between 1790 and 1840. And now we're going to use that model. Before I make some predictions with this model, let's just note that that base is about 1.03000. Very, very close to 1.03. That base is a growth factor. Every year on this exponential curve, we're multiplying by about 1.03 to get to the next year's value. That translates to an R value, R is base minus 1, of, I'll do it to full precision, but we can see what the result is going to be. My data is, my calculator is still in the current settings. So I just ran that exponential regression. And if I go to variables, statistics, move over to variables, statistics, move over to equation, I can select B, there's the base, there's the full precision base. If I subtract 1 from that base and multiply by 100 to convert it to a percent, I get what we can see there. To any reasonable number of decimal places, this is, I'll just write 3.00%, but it's actually 3.000%. So 3% growth, that's our growth rate. Annually, on this model, the population of the US is growing by 3%. So I've just answered part A on this slide. We're going to use this model. The answer to part A, the US population's annual percentage increase, we just got that. It's about 3%. To 3 decimal places, it's 3%. Now let's make some predictions, some future predictions. So we're assuming, if we were doing these predictions, if we had built this model prior to 1850, we would be trying to project into our future. Of course, we're in the future of this model. The 1850, 1860, and 1870 are in the model's future. So we're going to see, had this model been used to make predictions into the future, how would that model have done? So part B, we're going to make the predictions. Part C, we're going to talk about how well the model actually did. So let's look at 1850. In 1850, the t-value, we're measuring from 1790, so that's a t-value of 60 years after 1790. P of 60 is equal to what? Well, let's plug 60 into our model, y1 of 60 on the calculator. That's about 23.22. 23.22 million people. All right, so that's the first part of part B, predicting the US population in 1850, 23.22 million. Now, I'm going to go ahead and skip to the 1850 part of part C. How did that prediction come out? We know that according to the US Census, in 1850, the actual population was 23.2 million people. So the actual value is 23.2 million. So what is our model error? What's our 1850 model error? Well, it's equal to the actual value minus the predicted value. And that's equal to what? The actual value is 23.2 minus the predicted value, which is the y1 of 60. There. So this is 23.2 minus y1 of 60. And that's about negative 0.02. Negative 0.02 million people. Okay, I'm going to interpret that in a little bit. But that's the 1850 model error. What's the, I'll do it up here, what's the 1850 model percent error? Well, it would be the actual minus predicted, that's the error, divided by the actual times 100. So it's equal to the error that we just predicted divided by the actual population in 1850 times 100. Let's do that right here. There's the error, the actual minus predicted. Divide that by the actual, which is 23.2, and multiply by 100. That is about negative, I'll just round these to one decimal place, about negative 0.1%. 0.1%. Now, how did we do? Well, that negative, the 1850 model error, the average error of the model is, if we look back at a previous slide, the average error for our regression model was about 0.084 million. The magnitude of this 1850 model error is positive 0.02, and so the magnitude of this error right here is less than the average error. That means that in 1850, the model performed within the error of the model itself. This is a great prediction. 1850 came out very nicely. Had we used this model prior to 1850 to predict the 1850 population, it turns out we would have done extremely well, gotten a very good prediction. We can also see that from the percent error. The percent error is only negative 0.1%. The average error percent range that we came up with before was 0.49% to 2.2%. This 0.084 million average error translated to, over the data set, relative errors ranging between about 0.5% and about 2%. This 0.1 is definitely below 2.2%. It's even below the 0.5%. So it's extremely good prediction. Now let's do the rest of these 1860, 1870 as well. I could do the rest of the calculations kind of with this more manual process that I just did, but I realized, I've got a spreadsheet available to me. I'm going to do it that way. I'm going to go into my stat editor. Here I've got the data that went into my regression. I'm going to put the data points in addition to these data points in there. So 1850, that's a t-value of 60. 1860 is a t-value of 70. 1870 is a t-value of 80. So those are my 3 additional t-values. The corresponding actual values are 23.2, that's the one we just used, and 31.4 at t equals 70, and 38.6. Now for each of these I want to calculate the error, the model error for those years. So I'm just going to calculate all the model errors in L3. So I'm going to go to L3. Well, actually, I won't do the model errors in L3. To do the model errors, I need the model predicted values. So for all of these inputs, let's generate the model values, the model predicted outputs. That would be pointing to L3, doing Y1 of L1. We've done this many times before, so we know how to do it. Now we can see the model predicted values for all of the data points, including the last 3 that weren't included in the regression. And so now we can calculate all of the model errors, L2 minus L3, L2 minus L3. Actual values in L2 minus predicted values in L3. There are the errors. Remember, the first 6 of these errors go into the SSE, the sum of squared errors of the model. The last 3 are our new values. There's the negative 0.02 that we calculated right here. And now we can see that here, I'm going to build a table now over here. So 1850, 1860, 1870, those are my years. The t-value is 60, 70, 80 for those 3 points. The model predicted values, P of t in millions, for those 3 values are right here. Let's see, let me make sure I'm in the right spot. So at 60, that's the 23.22. At 70, the model predicts in 1860 a population of 31.20 million. And in 1870, when t is equal to 80, the model predicted value is 41.93. The error for each of those years in millions are right over here. Negative 0.02, that's the one we did on the previous slide, million. In magnitude, a higher error, 0.20, and in magnitude, a much, much higher error. The value is negative 3.33, but the magnitude is 3.33 million off. Okay? Let's calculate the relative errors. For all of these, I'm going to do the error in L4 divided by the corresponding actual values. Those are in L2. Those are our actual data values, times 100. Aren't spreadsheets nice? You can do lots of calculations at once. So now we can go down and see that when t is equal to 60, L5 has the relative error. There's the negative 0.1%. At t equals 70, the error is 0.6% higher. And then, bad news, in 1870, when t is equal to 80, it's negative 8.63%. Okay, so recall again, the average error for our model is 0.084 million, and that corresponds to, over the data set that went into that model, a range of about 0.49% to 2.2%. Now, in magnitude, the 1850 error is within that average error. That's gold. That's a beautiful prediction. When we go to 1860, the magnitude of that error, 0.2, is higher than the average error of the model. Here's the way I'm thinking of this. Here's our model. The average error you can think of as a plus or minus value on that model. So if we add 0.084 to the model, I'm exaggerating here, but if we add 0.084 to the model, we would have this slightly higher curve. If we subtract 0.084 from the model, we would have that slightly lower curve. The data points that went into that model are all between those dashed lines. When we went to 1850, the 1850 prediction was still within those dashed lines. The model performed in 1850 as well, if not better, than it performed over the data set. So that's beautiful. When we get to 1860, the error in magnitude is outside of those dashed lines. So the model's no longer performing as well as it did on the data set that generated it. On when we're extrapolating, and as we extrapolate, it turns out that our prediction is outside of the dashed lines. Our error is higher now. Now, relatively speaking, it's still a relatively low error in 1860, about 0.6%. It's still certainly lower than the 2.2%. So it's still not a bad prediction, but it's definitely not as good a prediction as we were getting within the data set. In 1870, we have really fallen apart. Now the magnitude of that, 3.33, is quite far away from the prediction. As a matter of fact, with that negative, remember, actual minus predicted. That means the actual value is under the predicted value. So the model is significantly over-predicting in 1870. And so that the magnitude 3.33 is way higher than the average error. And the magnitude 8.63% off is way higher than the relative error. So the model has fallen apart for our purposes. We did not get a reasonable prediction in 1870. Now I've summarized our results here in this slide. What happened demographically, to the U.S. population? It's kind of interesting when a model falls apart to think, is there something that happened that you could imagine would have an effect on the total population of the U.S., on the population growth? And as a matter of fact, the U.S. Civil War was fought between 1861 and 1865, and that is likely the major contributor of why the total population took a hit, and clearly the rate of growth took a hit there in those years. Now what I've done here, let's visualize. Note that I've put, remember, go back to Stat Editor, I put 3 additional data points into L1 and L2 that were not used to generate the model. So I could now look at a scatter plot of L1 and L2, and that scatter plot is still turned on, the model's stored in Y1. If I hit zoom stat now, we have to be careful when we read this. The first 1, 2, 3, 4, 5, 6 data points went into the model, into generating that model. The second 3 data points did not, the last 3 data points did not. And so we're looking at, these are extrapolated, the model, we're extrapolating, and now we can see how well our model did visually. That data point is very close. This data point is a little bit further off. This is just qualitatively what we saw with the errors that we calculated. And that third data point is significantly below, the actual value significantly below the model prediction. And in this slide, I have, so on our graph, this is what we're looking at. I went ahead and plotted some more points. I looked up the total population for a couple of more censuses beyond that, and you can see that the divergence of the actual values from that model is getting worse and worse. Basically, if you want to model the total U.S. population in this region, then you'll need to do a different fit. Maybe another exponential fit, but on data, from what we've got here, from about t=70 on, could be used to figure out a reasonable model for that era for the total U.S. population.